Welcome back. In this video, we are going to talk about proof of work. You might have heard that Bitcoin miners solve a computational puzzle. So today, you'll get to know what exactly is that puzzle. So first, let me summarize the previous video. We talked about the basics of Bitcoin and the details of peer-to-peer architecture and torrents. I will attach the link to the video in description so you can check that out. So there are three types of node in the Bitcoin. The first one is node OG, which keeps track of the entire blockchain from the beginning. The second one is node MG. It keeps track of the current transaction. To simplify, let's say node OG knows from the beginning and node MG knows only today. Node 3 is general users like you and me. So this node is not as important from technical perspective in this video. So let's say node A sends 20 bitcoins to node B. Now the OG node will validate the transaction, and if it is found legitimate, then it will be added into the mempool. But how does it actually validate the transaction? Let's say a node broadcasted a transaction among its peers and it reaches the OG node. The most important point to remember is there are more than 1,000 OG nodes, MG nodes and users in Bitcoin network. So as soon as the OG node receives a new transaction broadcast from its peers, it performs initial checks to ensure the transaction is well formatted and properly structured. The basic validation checks include, first one is syntax and format. So ensuring the transaction is correctly formatted. The second one is double spending. So before talking about double spending, the correct syntax and format means having proper serialization and valid transaction size. Double spending means checking the inputs of the transaction, that if they are already spent or not. Now we need to verify the signatures of the transaction using the public key of the sender. Fourth one is running the Bitcoin script to ensure that it executes correctly. The next thing is to check that the inputs provide enough balance to cover the output and the fees. And also the account has enough balance for that or not. So after all these verifications and checks, if the transactions are found legitimate, then they will be placed into the memory pool or mempool. So let's see what exactly is mempool. Basically, mempool is a part of your memory. Not this one, but your computer's memory. Just like each application uses some portion of your device's memory, Bitcoin Core does the same. And to make it efficient, it uses heap and priority queue data structures. We'll not focus on data structures for now. So to make it simpler, mempool is just a portion of your device memory. So let's say we have 4 nodes in the network. Each node will have different devices. Let's say few may have more memory, few may have less. So the size of memory pool will also be different for each node. Each node may not have the each and every valid transaction in their local mempool, but they can ask for it from their peers. Okay, so now the MG node collects all the transactions from the mempool and add it in a block and broadcast that block into its network. So this is known as Bitcoin mining. Let's now dive into it. First of all, let's talk about what does a block consist of, or block template. What is it? So the first thing which a block consists of is the block header. It contains the metadata about the block. The second one is transaction list, a list of selected transactions to be included into the block. And the third and the most important thing is coin-based transaction. This is the first transaction in the block which rewards the miners with the Bitcoin. And this is how new Bitcoins are added into the network. Let's now talk about the block header. This is where the actual crisp lies. As I talked that it contains the metadata. The metadata includes the hash of the previous block in the blockchain. The second one is Merkle root. It is a technique used to save the disk space. The third one is timestamp. It is the current time when the block is created. The next one is difficulty target or hash rate. A target which hash of the block must meet, and the last one is the nonce. This is a variable which miners change to find a valid block hash. To simplify, let's say if the difficulty target is 8, then the hash of the block must start with 8 zeros. So you keep iterating and changing the nonce until its range is exceeded, and then you change your block number or the data. Here's a diagram of Merkle tree. So let's say you have many transactions. One block can consist of 20,000 transactions in Bitcoin. So you'll have to store these many transactions, and it will occupy a lot of space. So to save the space, we use this Merkle tree data structure. So as you can see, we have all the transactions. So instead of storing the transactions as it is, we take the hash of the transactions in pairs. So first of all, we'll take the hash of 2 transactions. Similarly, for each transaction, we'll compute their hash. Then we'll take the hash of 2 transactions, and similarly, we'll have a root node which will be the hash of the complete tree. From that root node, we'll be able to get all the transactions whenever we require. So that is why the Merkle tree is used. So let's get back to the demo. So as we talked about the components which a block consists of in Bitcoin. So first one is the block number. As you can see, it is unique for each and every block. The second is the nonce, which we talked about. It is the number which the miners keep changing to get the perfect hash which satisfy the difficulty target or the hash rate of the block. And the third one is data. As you can see, the current difficulty target of the block is 4. So we can see the hash of this block starts with 4 zeros. As soon as we try to change the data or anything within this block, the whole block becomes invalid. And as you can see, the hash of the block is not starting with 4 zeros, which is our difficulty target. So this block is not valid. So you will now keep changing the nonce to see if the hash of the blocks become what is needed, but it will take a lot of time. So that is why it is said that mining requires a lot of computational power. So as you can see, when we click on the mine button, our hash is calculated and the block is validated. But as you can see, the difficulty target is just 4, which is pretty easy. So it took this much amount of time. But if we keep it as 8 or 10, this is just for example's sake, then it will take a lot of time to find the perfect nonce. So if we set the difficulty target to 8, let's say, then it will be out of my computer's range to find the perfect nonce. So all the blocks put together, we form a blockchain. So here also we have the block number, nonce, data, the hash of the previous block, and the hash of the current block. The data part here can be the hash of that Merkle tree we talked about. So as you can see, each block consists the hash of the previous block. So it is pointing to the previous block. The hash of the first block which it contains is 00 because it is the first block in the blockchain. And if you try to change anything Let's say you're trying to change anything in the first block, then the whole chain will become invalid. Why? Because the hash of that block will change, and similarly the hash of next block which is pointing to this will change, and similarly for others. So this is how blockchain works. You have to find that nonce which satisfy this block's criteria. And once the size of that nonce is exceeded, you try to change the other part, such as the data or the block number. Then you'll have to start mining once again from the beginning. So in real life, in case of Bitcoin and the given difficulty target, it takes a lot of time and a lot of computational resources. The most important point to remember here is the difficulty target of the blockchain or the network, it keeps fluctuating compared to the previous target. So as you can see, this is the example of tokens. You have block number, nonce, and the transactions, hash of the previous block and hash of the current block. Here you can see the coin-based transactions. So how Bitcoins, newly created Bitcoins come into the picture. So this is how it happens. As soon as a block is mined and broadcasted into the network, the nodes will try to validate that block using the same rules and checks which were used to validate a single transaction. And the hash of the block meeting the criteria of the difficulty target is the proof that miners has done some work. So this is proof of work. See you in the next one.